Okay, so here we're looking at number 1 from Miscellaneous FRQs, AP Review. This one is going to be evaluating a derivative graph. So we're looking at, let's read the instruction here. Continuous function f is defined on a closed interval from -6 to 5. The figure above shows the portion of the graph of f consisting of 2 line segments. So we have 2 line segments here. And we have a quarter circle centered at 5, 3. So we're going to imagine this is the center of the circle, and here's the quarter circle showing. The rest of the circle is not showing, just this quarter here. And we're given that order pair that sits on the graph is 3, 3 minus root 5. Okay. So we know that the depth integral from -6 to 5 is equal to 7. So -6 to 5, we see 5 here, but we don't see all the way to -6. So there's this huge gaping hole that we don't have anything visually to know what's happening, except for the fact that when all the regions are added together, we're getting a value of 7. Okay, so that's something to take note of, that there's a missing portion that we don't see on the graph. We're asked to find the value from -6 to -2, so that's what we're asking. We're given this whole, given what this whole sum is, and we're asked to find this portion, and the only thing that we have to work with is this portion here. So let's start off by creating an equation that we know to be true. If we want to find that full extent from one end to the next, from one end to one end, from -6 to 5, we can think of this entire region as the region from -6 to -2 plus the definite integral from -2 to 5. Okay. So once we have the statement created, then we can kind of break this down piece by piece. We know that definite integral from -6 to 5 is equal to 7. We have that full region given to us. We're looking for this definite integral from -6 to -2. So if we can figure out what this piece is, then we should be able to combine and bring everything over to one side and solve for this like as if it was a variable. Okay, so let's focus our attention on the definite integral from -2 to 5. So -2 to 5, we can think of these as all geometric shapes that we can derive from, area from. So that's a triangle, 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 triangle. Here we have a square, here we have a triangle. And this portion is not by itself a geometric shape, but if we think of the fact that if we can visualize that this is a square and there's the quarter circle, and if we take the square and if we subtract out this this quarter circle, then we're left with this curved region here. Okay, so let's move from left to right here. 1/2 base times height, that's going to be 1/2. This region here is -1/2, so these will cancel out. These two regions are the same. They're both 1/4. One is above the x-axis, the other region is below, so those will cancel out. So everything so far has canceled out to be 0. This is 1. This is 1/2 base times height. 1 times 2 divided by 2 is going to be 1. And this region here is a square minus a quarter circle. So the square, this large square, it has area of 9. 3 times 3. 3 squared is 9. And then the quarter circle is 1/4 pi r squared. So the radius of this quarter circle is going to be 3. So 1/4 pi radius squared. And we get 9 minus 9 over 4 pi. So that is this region here. So if we combine all that together, we get 1/2 and 1/2 cancels out, 1/4 and -1/4 cancels out, 1 plus 1, square plus triangle, plus the square minus a quarter circle, which is 9 minus 9/4 pi. So that's going to clean up to be just 11 minus 9 pi over 4. We bring that over to the other side to combine it with the 7. So we get 7 minus 11, which is -4. -4 plus 9 pi over 4. And that is the resulting value of the definite integral from -6 to -2, the portion that we're not seeing here. Okay, number 2, part B, rather. Find the definite integral from 3 to 5 of 2f prime of x plus 4. So I like to, anytime I see a plus or minus, I like to think of these as two separate expressions, and then I can kind of break apart my definite integral expression. So I can think of this as a definite integral from 3 to 5 of 2f prime of x plus the definite integral of 4 from 3 to 5. So this piece we can apply using power rule, right? Antiderivative. If we antidifferentiate 4, we get 4x. We plug in the upper and lower bound, we get 20 minus 12, which is 8. Now moving on to this portion here, we have to apply first theorem of calculus, which says that the antiderivative of f prime from a to b, f prime will move up a level to f of x, and then we plug in our upper bound minus lower bound. So let's apply that for this notation here. So antiderivative of f prime becomes f. We plug in f of 5 minus f of 3, and now this is helpful because we do have in front of us our f function. So to find f of 5 and f of 3, we just locate the ordered pair. So f of 5 is 0, and f of 3 is hard to pinpoint, but we are given that information, so we can use that y value, 3 minus root 5. So we plug that in. F of 5 minus f of 3 is equal to 0 minus parentheses 3 minus root 5. There's a 2 coefficient in front, so we have to multiply that 2 through. There's a plus 8 from the result of the second definite integral. And we're left with 2 times negative 3 plus 2 times root 5 plus 8. Combined like terms, we get 2 plus 2 root 5. All right, part C. The function is given by g of x is equal to the definite integral from negative 2 to x of f of t. Find the absolute max. So absolute max, absolute min, we're going to be applying extreme value theorem. So extreme value theorem says find the critical points, and then once we find critical points and we locate the endpoints as well, then we test our endpoints and our critical points back into the original function and test them to see which one produces the largest y value and the smallest y value. But in this case, we're only looking for the absolute max, so it's just the highest y value. So this notation, also want to point this out, this notation indicates that this f of t is sitting one level below g, because the antiderivative of f will bring the f up to be equal to the g of x level, which means that the f is really sitting at a derivative level below g. So whenever we see this notation, we just have to verbalize the fact that this is really a notation for saying that the f is really a g prime. This is really a g prime graph. Okay, really a g prime graph. So if we think of this as a g prime graph, then we can go with all the information that we know about a derivative graph, right? That anything above the x-axis represents positive slope, anything below represents negative slope, anything on the x-axis represents a slope of 0. So the critical points are going to be the x-intercepts, which will just be -1 and the 1/2. And we know that the graph is going to be rising with a positive slope above the x-axis, then below the x-axis, negative slope, and then positive slope again. So we know that there is a relative max at -1, there's a relative min at 0.5, but we're trying to look for the absolute maximum, so we only have to test the relative maximum, because we know relative min can't be anything dealing with the maximum, and test the endpoints. So we'll test -2, -1, and 5, and they all go into our definition for g of x, which is the definite integral from -2 to x. So we go from -2 to -2. Anytime the bounds haven't moved or they're matching, we know that area is just going to be 0. So the integral from -2 to -1, so -2 to -1, that's a positive 1/2. So we can put 1/2 in for that. And then the integral from -2 to 5, integral from -2 to 5, we gathered that information from before, right? That definite integral from -2 to -5 is going to be 11 minus pi over 4. So 11 minus pi over 4, if we think about that value, that's really 27 over 4, which is around 8 or 7 or 8. And so 11 minus 7 will give us 4. 4 is greater than 1/2, is greater than 0. So we know that our absolute max value is going to be this 11 minus 9 pi over 4. Part D, evaluate the limit. So the first thing we do when we evaluate the limit is plug in that x value and see what that gets us. So 1, let's plug in 1 for all the x's. We get 10 to the first power minus 3 f prime of 1 all over f of 1 minus arctangent of 1. So f prime of 1 is just asking for the slope of the f graph at 1. So the slope of the f graph at 1, this is a linear graph, so we can just do rise over run. Up 2 over 1, this is a slope, a slant of 2, so slope of 2. F of 1 is asking for the order pair, so order pair of f of 1 is going to be directly at 1, so put that in for f of 1. Arctangent of 1, when is arctangent equal to 1? Arctangent is equal to 1 at pi over 4. So then we have 10 minus 6, which is 4. 1 minus pi over 4, we leave it in that form. So any of these variations are fine. We're just trying to, I just worked my way down so that the complex fraction is resolved, but this is an acceptable answer as well.